Our last topic of this chapter is vapor pressure, and vapor pressure is this idea that if you have a liquid and you put it in a container, so here's our liquid down here, it is constantly evaporating. And if you've ever gone ahead and you've put your nose above, say, a bottle of something stinky like a perfume or aftershave, you can smell it pretty nicely. What's going on? The molecules are constantly moving around in the liquid, so that's that kinetic molecular theory. But every now and again, one of those molecules can move towards the surface and can break free. And when it breaks free, it forms a gas. And we can measure the partial pressure of this gas of the liquid. So this might be the partial pressure of your aftershave or your perfume. And we call this the vapor pressure. And sometimes we're kind of lazy and we call that VP, which is much easier. And of course, if we leave the top off, then eventually all that liquid will evaporate. So my cup of tea, if I leave the top off in a couple of weeks, I hope I didn't leave my tea in my office. Anyway, there'll be sort of a brown stain on the bottom of my cup and all the water will be gone. But if I went ahead and put a cap on it, then eventually that pressure would reach a maximum value, and that would be called the vapor pressure. We know that if you take something like alcohol and you heat it up, or nail polish remover in your hot hands, it evaporates more quickly. So in general, the vapor pressure increases with temperature and decreases as you cool it down. So as you put things in the freezer, the amount of vapor they give off is much, much lower. And so your liquid doesn't evaporate nearly so quickly. In chemistry, we talk about volatility. And volatility, we normally if people like explode or can't take a joke and get very mad, we might say they're very volatile. Or in movies, right, we might think of something's explosive, it's very volatile. But it turns out that's actually not the chemistry definition. And the chemistry definition has to do with vapor pressure. And so the more volatile something is, the more vapor pressure it has. So more volatile liquids have a greater vapor pressure. And if you think about liquids, and you think about something like olive oil. So olive oil, if you've ever dealt with olive oil or motor oil actually, or anything like that, the vapor pressure is pretty low. If you smell it, it really doesn't have much of a vapor at all. And if you take something like water, water's kind of somewhere in between. So, it takes a little bit for the water to evaporate, but you definitely get some vapor above here. And if you take something very volatile, I'm using that word there, I probably shouldn't, like a nail polish remover, which is acetone. And normally in class, I throw some acetone on the board, and the acetone just kind of like vaporizes instantly. And so it evaporates so quickly. If you put it on your hand, it actually cools your hand off as it completely evaporates in a few seconds fast. So we say that this is very volatile. So this is very volatile. And on the other end, we would say things like oil are relatively non-volatile. So they barely have any vapor pressure at all. And water is something intermediate. So it's fairly volatile. We know that cups of water will evaporate over hours or days. We know that small ponds will eventually evaporate if there's no rainfall. But it's not super volatile like gasoline or acetone, where if you spill it, it's gone in a few minutes flat. Now, one of the reasons I think vapor pressure is very cool is that you can draw these vapor pressure versus temperature diagrams. So I'm going to draw temperature here. I could write degrees C, I suppose, and vapor pressure on my vertical axis. And it turns out that these diagrams are exponential. So just like the spread of COVID-19, the vapor pressure increases exponentially with temperature. So it's really kind of scary, actually. So at low temperatures, right, the vapor pressure barely goes up, and then you get to a point where it just keeps doubling every few degrees, and you just get this massive, enormous rise in vapor pressure around a certain temperature. And so what does this tell us? Well, it turns out something kind of cool. If we take our vapor pressure of 1 atmosphere and we draw a horizontal line, we can ask ourselves at what temperature does our vapor pressure match atmospheric pressure? And it turns out for something like water, this matches at 100 degrees Celsius. And if you ask yourself what's going on here, it turns out when your vapor pressure matches atmospheric pressure, the vapor can actually sort of explode out of the liquid and push back the air. So when your vapor pressure is equal to air pressure, and on a normal day, air pressure is 1 atmosphere, essentially you got this phenomenon called boiling. And so things boil when their vapor pressure matches air pressure. So this is the boiling point. Actually, 1 atmosphere and 100 degrees C, we refer to this as the normal boiling point, or NBP for short. And this is the temperature when the vapor pressure is equal to 1 atmosphere. So for every liquid, there's a different temperature where the vapor pressure matches 1 atmosphere, which would be the air pressure on a normal day at sea level on an average place on the Earth. And that corresponds to the normal boiling point. And what I think is kind of interesting is if you go maybe to Boulder, Colorado, where it is maybe a mile high, and if it's a mile high, that means there's a mile less of air above you. That means that the air pressure is actually not 1 atmosphere. It is maybe 0.9 of an atmosphere. And if you read on down, you'll see that the temperature there is much lower. Maybe at this point here, it's 88 degrees C or something. I'm just making up numbers, so I'm not quite sure what it is. But it turns out that if you're at high elevation, your water boils at a much lower temperature. So it's kind of naughty to talk about boiling point, because boiling point depends upon air pressure. So although we say water has a boiling point of 100 degrees C, in colloquial speech, we should probably say the normal boiling point of water is 100 degrees C, and that's when it has a vapor pressure of 1 atmosphere. But if you live at high elevation, then water boils at a much lower temperature, which is a problem because the temperature is what cooks your food. So if your temperature is lower, then you've got to cook the food longer. And if you have something like an Instant Pot, then the Instant Pot works by increasing the pressure inside, so it actually lets the pressure boil, or increase rather, to a higher value. It doesn't let it get too high, otherwise that's called a bomb. But anyway, if you let your liquid boil at a higher pressure, say 1.1 atmosphere, and you can see at what point on the vapor pressure curve would it be this? Well, maybe it's something like 108 degrees C or something like that. So the higher the vapor pressure, the higher the air pressure inside the container you're trying to boil it in, the increase or the higher the boiling point is. So an Instant Pot cooks food much faster because an 8-degree increase in temperature maybe cuts your cooking time by a half. And if you're sterilizing surgical instruments in a hospital, you might use something like a autoclave. And in an autoclave, basically you allow the steam to reach a much higher pressure, and that means everything boils at a much higher temperature, which helps to cut down the sterilization time. I read a book last summer actually that talked about chloroform, and chloroform was one of those early anesthetics, and Queen Victoria actually had chloroform, I believe, when she gave birth. It kind of dulled the pain. And one of the dangers of chloroform, and the reason they don't use it, or they find safer alternatives, but one of the reasons it was so dangerous originally is that depending on the temperature of the room you would give the chloroform in, it would have a different vapor pressure. So on a colder room, right, it would have a lower vapor pressure. On a warmer room, it would have a higher vapor pressure. And it turns out you need a little bit of chloroform vapor to sort of dull the senses. But if you have too much, then it actually is really bad for you and will kill you. So they didn't realize that this curve is an exponential curve. And the lower the temperature, the lower the vapor pressure. So if you didn't need to deliver a lot of the vapor, that was good. But if you did use chloroform in a warmer environment or in a warmer hospital room, it would actually be a bad thing because it would give off more vapor and potentially kill you. Uh-oh.